Now, what we saw in that first movie, in other words, the gradual appearance of that orangey brown color, is not what you typically associate with a clock reaction. A clock reaction is, of course, one in which you mix the reactants. So there they are mixed, and then nothing happens, and then suddenly something happens and it goes that blue or that black solution. Okay, and you should be aware of the fact that that is because we got the same reaction here, except the triiodide, or again, effectively the iodine mixed with an iodide. In this case, we're not following its orangey brown color. We're using the fact that when you have starch in there, triiodide forms a lovely complex that's colored blue. Now, again, I'm being a little bit pedantic here, more than you need for the A-level. You're told it's an iodine starch complex. It's actually more complex than that. Two of those triiodide anions come together to make two new anions, an I5 anion and the iodide anion, and it's the I5 minus anion that is the one that complexes with the starch. Now, trouble is, though, that if I just did the reaction like this with the iodide, hydrogen peroxide, acid, and popped in a little bit of blue, then it would go blue almost immediately, okay, because that starch complex, it's a very, very deeply colored complex. The fancy word for that is it has a very high extinction coefficient, and so pretty much as soon as you do the reaction, as soon as you start making some of the triiodide, boom, it's going to go blue. And that, of course, is not what we want. We want it to do nothing for a little while and then suddenly go blue. And what we do with that is we put in the components of a competing reaction with which you are familiar. We put in sodium thiosulfate, of which the important component is, of course, thiosulfate, S2O3 2-. By the way, something I try and get stuck in my students' head is that when you see thio or thia in anything, it means sulfur. And so thiosulfate is where we take sulfate, SO4 2-, and we replace an oxygen by thio or a sulfur, giving us S2O3 2-. Anyway, you've seen S2O3 2- because it reacts quite happily with iodine, again showing this as the triiodide, to reduce the iodine to make iodide. Okay, so in this particular reaction here, what we do is we add in a limiting amount of thiosulfate. So we have everything together, we mix it all together, the reaction goes ahead and makes the triiodide or the iodine, which immediately is snaffled up by a thiosulfate going back to the iodides. Those iodides meet with another peroxide to make some more triiodide, which is immediately snaffled up by more thiosulfate to go back to the iodide. And so only when the thiosulfate is all used up. At that point, then the starch can come in, grab one of those triiodides that is now no longer being snaffled up by a thiosulfate, and you make the blue. Okay, so mix the reactants. Nothing happens, apparently, because any triiodide that is produced reacts with the thiosulfate and goes back to the iodide. Nothing happens because triiodide goes back to the iodide because it reacts with the thiosulfate. And then when that thiosulfate is used up, that's what we mean by limiting amount. When that's all used up, now suddenly the triiodide could get together with the blue starch or together with the starch to make the blue complex. And that's the reaction that you did at A-level, and that's the reaction that makes up our second part of the reaction. Little note here, okay, with a smiley face, just indicating that, of course, you think about it. You have to be careful not to have too much thiosulfate in there, because if you end up using up all the peroxide before you've used up all the thiosulfate, it never, ever, 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 ever goes blue. So let's talk about what we actually did in the lab. Okay, so you had a series of mixings to put together. We had 4 different solutions. When you're doing this yourself, you do all 4 of these. The idea was that to save time on our A-level day, one group did the mixings for 1, one group did the mixings for 2, one did the mixings for 3, one did the mixings for 4. Now, the whole idea of this is that we do the reaction with different concentrations of the iodide and the peroxide so that we can study it consistently and determine the rate law of the reaction. Now, in order to do that, remember, of course, we needed to put in the acid there. That's another reactant. We also, most importantly, needed to put in the thiosulfate, because we don't get that blue color. In other words, we don't get something we can time until all the thiosulfate has been used up. Now notice each time I'm using the same amount of the thiosulfate. So that means that while I wouldn't have to do that, I could still do the calculation appropriately. Otherwise, it makes things a little bit easier. In the same way, I use the same amount of the sulfuric acid each time. Notice that this is going to be in massive excess because it's 1 molar sulfuric acid compared to 0.1 molar peroxide and the potassium iodide. I should also note at this point that the sodium thiosulfate, remember, had to be limiting. Look at its concentration compared to the concentrations of these. So massive excess of the sulfuric acid, the same each time. Massive deficit or limiting amount of the thiosulfate, using the same each time. And notice I use water here to add up the total volume, so it too is the same each time. Again, that just makes the calculations easier. Now notice what I'm doing now with the important bits, okay, with the peroxide and the iodide, because when it's all said and done, my rate law is going to have something to do with the concentration of the iodide, something to do with the concentration of the peroxide. So I do the experiment first of all, and then I change one thing at a time. So as I go from experiment 1 to experiment 2, I've got the same amount of iodide, but I've halved the amount of peroxide. As I go from experiment 1 to 3, I've got the same amount of peroxide and I've halved the amount of the iodide. And then just for experiment 4, several ways you could think about this. Going from experiment 2 to 4, I have halved the other one, the iodide. Going from experiment 3 to 4, I've halved the peroxide. Or as we will use in our calculations later on, we can notice that going from 1 to 4 via the steps of 2 and 3, I've ended up halving both the peroxide and the iodide, although of course I'm not being naughty there, changing one thing at a time, because each of these steps just changed one thing at a time. Now, I then did this reaction, or you did this reaction, but we're going to use the data that I got when we did this reaction and measure the time taken for the solution to go blue. And there are those times. Okay, so here are the data that we're going to use for the rest of this particular movie. So clearing a bit of space for ourselves, there are the data. That's what we did on the previous slide. And also I started doing the calculations for you on the data sheet, because we've got our volumes of the peroxide and the iodide and the thiosulfate, but of course the volumes themselves aren't what we need. We need the concentrations, so we need to calculate the concentrations. And then we also need to determine the rate of the reaction, because the rate law is equal to rate equals K times the concentrations of blah, 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 blah. Okay. So how did I do these calculations here to get the concentrations? Well, I use your favorite old equation, C1V1 equals C2V2. So let's do that for the peroxide, which actually also happens to be the same for the potassium iodide. I started off with 5 mils of 0.1 molar H2O2. And I diluted that by adding more of these liquids until I had a total volume of 20. So C1 was 0.1, CV1 was 5, C2 we don't know, that's the new concentration of the peroxide, but I do know that the volume of that new concentration was 20 mils. So pop that around, C2 is equal to 0.5 divided by 20, C2 equals 0.025. And I can do those calculations with that for the rest of these. For the thiosulfate, again, we're using C1V1 equals C2V2. The thiosulfate, I started with 2 mils of a 0.005 molar solution, which again was diluted to 20 mils. So C2 in this case is going to be 2 times 0.005, which is 0.01 divided by 20, which is the 0.0005 there. Finally, what's the rate? Well, the rate is change in a concentration over change in time. And what's actually changing in terms of that concentration that's easy to know is the thiosulfate, because as soon as the thiosulfate is gone, the blue color appears. Other way to say that is the blue color doesn't appear until all the thiosulfate has gone. So our rate is just going to be how long did it take, delta T on the bottom, over the concentration, all of the concentration of thiosulfate to disappear on top. Because we used the same volume of sodium thiosulfate, the same concentration and the same total volume, the change in the thiosulfate concentration will always be the same. It'll always be the 0.0005 molar. For this first reaction, the time taken was 38. So the rate is 1.32 times 10 to the minus 5. So now you can go away or pause the video and complete this data table, right, using all of these other concentrations. Now, just like Blue Peter, that's what I've done on this slide. So now there really wasn't room to keep all the volumes and so on. So you just have to either take my word for it that this is what was calculated, or have done it yourselves. But you can see here's the concentration for experiment one, the peroxide, the iodide, the sulfate, and then the rate, that's the thiosulfate divided by the time, doing the same thing for 2, 3, and 4. Now, going back to what we said earlier, when I went from equation 1 to equation 2, or experiment 1 to experiment 2, I halved the peroxide. Okay, and as I halved the peroxide, let's see what happened, right? Same iodide, same thiosulfate. Look what happened to the rate, 1.32 divided by 6.67, 10 to the minus 5 on top, 10 to the minus 6 on the bottom. That is halved, okay? 6.67 times 10 to the minus 6 is half of 1.32 times 10 to the minus 5. Just check it for yourselves, putting it in on your calculator. So as I go from 1 to 2, halving the peroxide, I halved the rate. So in a simplistic sense, whatever I did to the peroxide, I did to the rate. That means it's first order in the peroxide. Now again, going from 1 to 3, so 1 to 3, I halved the Ki, right? Got from 1 to 3, we got the same peroxide, we got the same sodium thiosulfate. The difference is I have halved the iodide. And what's happened to the rate is, again, I have halved the rate, okay? 1.32 times 10 to the minus 5 is twice 6.49 times 10 to the minus 6. Again, prove that to yourselves on your calculator. Notice it's not exactly 0.5 or 2, depending which way around you did it. But of course, this is an experiment. It's close enough for it to be. So again, half Ki, half the rate, first order in Ki. Now that would be enough to finish with, but we did do experiment number 4, in which we, as again I said previously, you could think of that as going from 2 to 4, keeping the peroxide the same, halving the Ki, or going from 3 to the 4, keeping the iodide the same, halving the peroxide, or as I'm going to do here, overall from 1 to 4, you've halved both of them. Now, if you halve one and you halve the other, what you would expect to happen to the rate is a half of a half, which is a quarter. And indeed, that's exactly what happens. 3.34 times 10 to the minus 6 is a quarter of 1.32 times 10 to the minus 5. So that is in agreement with first order in both. Thus our fundamental rate law here, ignoring the H plus because I wasn't interested in the H plus at this particular stage. Rate is K, rate constant, times the concentration of H2O2 to the power of 1, because it's first order, times the concentration of the iodide, or potassium iodide, however you'd like to put it, raised to the power of 1, because that too is first order. Final thing that we can do, you don't have to do this in order to determine the rate law. This is the rate law because, of course, K changes its value as the temperature changes, and that's indeed what we'll investigate in the next part of the experiment. But we might as well determine K for our situation here. Now, I'm not expecting it to be perfect because we made no attempt in this first particular run through the reaction to control the temperature, but it's not a terribly endo or exothermic reaction, and all of them were done on the bench top at the same time in the same conditions. So it's a reasonable assumption the temperature didn't change. So how am I going to calculate K? Well, I just pop the values in. So for the first one, rate 1.32 times 10 to the minus 5 equals K times the concentration of H2O2, 0.025, times the concentration of iodide, 0.025. Pop that in, and K is 0.0211. Do the same for all the other ones, because if you've got all these data, you might as well calculate K from all of them. for two reasons. The first is it gives you a little check on your calculations and indeed on your rate law. But the second thing is, the more data you have that you can average together, the more likely it is that your reaction is as precise and as accurate as you can get it. So anyway, there's our 4 values of K. Notice a little bit of variation as one expects for experimental values, but really not too bad. Average those together. K is 0.0212. Now the units, well, we're saying it is a second order reaction here. The units of a second order reaction's K, 1 over concentration times 1 over time. Or you can get fancy and you do liters per mole per second, but I prefer just to have molarity to the -1, seconds to the -1. Pop that in, and there is our final rate law. Rate is 0.0212 times the concentration of peroxide times the concentration of iodide. Next video, we'll do the same reaction, but now we're going to do it at different temperatures in order to illustrate the Arrhenius relationship.